Okay, so what I want to try to figure out today is how do we get that train at all? I'm not gonna feel like I just, this is definitely something that is currently kind of working. Every time I run it, it just gives me a different but that's because the projections and all the stuff is randomly initialized, right? So the sort of the K, Q, V matrices and all this kind of stuff. And so obviously this weights don't really represent that. So now we knew what I need to figure out now is how do we actually train that thing? So my only question is what have we really done, right? So in our main file, we essentially do, so we have a sentence, okay? We tokenize the sentence, then essentially what we're doing is we do the positional encoding, the multi-headed, and then the multi-head attention is kind of what does these attention, like calculates all this attention stuff, right? Obviously this needs to be trained somehow. So how do we train that? So the architecture diagram that we have is this one. So my guess is we've done the input embeddings. Like my current guess in my head is like we need training data, right? So we need like inputs and outputs, right? We need input sentences and output sentences, because that's what you need to train them on, right? And I'm not so sure if this positional encoding and this masked multi-head attention is the same thing. It seems like if I look at the attention function, there is this mask in here, which is a know what this mask is doing. So, but it seems like Ghostwrite already gave me this code so that it will be reusable somehow for these. Then we're doing the normalization, and then I don't know. But I have no idea what these feed-forward boxes are. So let's ask Ghostwrite. So we have, so we now have one input sentence. We have implemented the position encodings, and we have also implemented the multi-head attention. What are we missing so that we can actually train the different matrices like K, Q, V, the attention weights? So, okay, so we need a loss function. Kind of, yeah, that made sense. That makes sense, and a way to compute gradients with respect to the parameters of the model. We also need to initialize the matrices randomly, as they're currently defined randomly, and then perform backpropagation to update the values of the matrices based on the loss. Once we have performed multiple rounds of this process, we can use the updated matrices for prediction on new input sentences. Exactly. In the architecture diagram, there's a feed-forward box. So in the transformers architecture diagram, there is a feed-forward box. What is this, and do we need to implement it? So this is responsible for performing a point-wise fully connected layer on each position separately and identically using different parameters. It has two linear transformations with a rel activation in between. The layer helps in capturing the interactions between different tokens. We can add the feed-forward layer as part of the transformer, but it is not necessary for a basic implementation of the model. Okay, that's good. So we can probably keep it out for now, then we'll add it later. We can train the model on its existing layers and add the feed-forward layer later if required. Okay. That is good. I guess the same here, right? So I guess so. Let's get started. So let's get started. What needs to be implemented based on your response is a loss function. And gradient calculation. So where do we start? Where do we start in main pi? Okay, cross entropy loss. So let's see. Let's see. So we'll need to start by defining the loss function that we want to optimize during training. Since this is a sequence-to-sequence problem, a common choice is the cross entropy loss. You will need to define this function, which takes as input the predicted output tensor and the target output tensor and outputs the loss value. After that, we'll need to compute gradient of the loss with respect to the trainable parameters in the model. We can use automatic differentiation provided by PyTorch. This is where I'm thinking. I'd like to go as from scratch as possible. I'm not so sure if that's a rabbit hole I should go down to. Whether I can do these differentiation by hand or just use what PyTorch uses. And we need the backward method inside multi-head attention, which does the back propagation. Additionally, you need to find some way to apply the gradients to the model parameters, usually done with stochastic gradient descent, and so it's right. So okay, a lot of homework. We can then use these parts to train a model, really performing. Okay, so can you summarize the tasks above in the list? Can you summarize? Because I wanna store that maybe. So next steps. And have that in there. Can you do it? So I'll keep it as markdown. Can you really write the list above? You have to be very specific. Well, there's no markdown. That's not markdown. I mean, maybe just in markdown and just actually rendering it. Whatever. Use the code box so I can copy it. Copy the markdown. There you go. It's cool. So next steps, at least we have it like this now. And okay, so we need a cross entropy function. Then we need a gradient loss. It's funny because it seems quite impossible that that's it in terms of that's all what you need really. So he gave me like an actual cross entropy loss function, right? So for the cross entropy loss function, to update the codes. That seems to be very high level. Red and target. Tensor of shape, batch size. We should probably add the batch size now. Probably we should add the batch size dimension to all this stuff. Because we currently just have we just process one sentence. So that's definitely not ideal. Then we just want to add that extra dimension to have multiple sentences. compute cross entropy. So let us maybe, before we go ahead, let us just add the byte size to the code. So currently, let's do, yeah, because I think that otherwise we're gonna get into trouble. So can you help me adapt the code so that it supports multiple sentences by a predefined byte size variable. So okay, so it's actually quite cool because it's really, let's do this slowly. Okay, so it actually took the right file. That's pretty cool. And it seems like the problem with the length of the output is gone. So let's say byte size 4. Okay, so let's do this. So byte size 4. So now we have all these sentences. And now essentially what we need goes right. So we need to tokenize the input sequences. Shouldn't we actually change that? That hasn't, let me put it side by side. No. So Ghostwrite is telling me, okay, so now we have, yeah, I think we need to wrap that tokens. Yeah, it's yet another dimension. I don't know why they use word sentence for word in sentence. Okay, so now it's yeah, okay, now it's correct. Okay, so words, it's sentence for sentence in sentences, and words. So it's actually iterating over sentences, right? So if I print tokens here right now, when sentence was just 1, right? So when it was like sentence, so when sentence was one thing, then the output was what is wrong? It's because of the indentation. This is Python. No. Stupid. Okay. So this just prints, oh come on. Sentence is not defined. Sentence is not defined. So I want to make sure that it's correct. So this essentially just gives you one sentence with like the different words. And now what we should have is if we remove these and we basically copy this code here, the tokenization, okay. So now we should just have the let's print a shape. Of course, the rest doesn't work now because it's not adapted for these, right? So I need to keep adding. This is no shape. length. It's not like that, it's like this, isn't it? In Python, it's got a length of 4, which is the sentences that we have, and each sentence, so the length of 1 is then 15. Yeah, that's correct. Okay, cool, so that's fine. Now padded tokens. Sentence for word in sequence for sentence sequence in tokens words. Oof, 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 oof. Is this correct? So this should give me, so essentially if I comment this out and print padded tokens, what is this supposed to do? It's supposed to pad the tokens, but it's not padding them, right? The model is supposed to pad the tokens, but it's not padding them. Give me a second. So for sentence, what is sequence in here? Is it tokens and words? What the heck is this? We just, I don't think that's correct. I think all we want to do is we just want to add another dimension to these, right? So for word in tokens, sentence in words, it's the same like here. I think that that's all we want is these, is add another here for word in sentence, so for word in sentence, right? And then for sentence in tokens, exactly, right? So we want, okay, let's see if that's yes, that's correct. So it's padding each thing. Okay, that's correct. Now cast the nested list to an NumPy array. But now it's a list of lists, right? So tokens. Can you do this? That's just an array. So padded tokens. Again, it's the same. It just add one more level for list and sentence for sentence and parrot tokens. So each parrot tokens has sentences, and then it's sentence, then you do the whole thing later. Yeah, exactly. So now we want to print this in here and put a this. And this is now I should be able to run the shape of it. But yeah, essentially that's it. Makes sense. So if I do this shape, it will tell me that it's four. So it's a bunch of 4, and then each of them has 15 words, and each word has depth 10. Yeah, correct. So at least we got that. Cool. And now we need to make sure now we need to make sure that nothing breaks, and that actually the positional encoding has that as well. So we need the batch size, right? We need the batch size. Do we need a batch size? Do model max length? So what is positional encoding doing? I would actually need to do that for each max length D model. Yeah. So actually rewrite these. So that it includes batch size. And that's kind of correct. It adds batch size, it adds an outer loop, and then this B. That is correct. I think that is correct. So batch size is at the end. Exactly. So this would be this. This would be this. Maybe. And then I think if I now go here and print X, should be okay. Well, we need batch size. So we need batch size. Yes. Let's print the shape. Should have that 4 in front of. Yes, correct. Okay. And now multi-head attention. So now I guess this doesn't matter. This probably stays the same. It's this is what matters. So and because here we have more dimensions by size. Yeah. Yes, but I think I have to leave it here. So the next is okay. So the next is here. So add the batch size to do. So this is important because if we don't get the batch size in there, then we're not going to be able to train these. Can I format these again nicely? Exactly. And to be honest, that is kind of inputs, right? But we need outputs as well. I don't know how we're gonna marry those things then. That's kind of my next. So this is the rest is to kind of do it for the multi-hypertension, yeah. But then, yeah, that's gonna be interesting, right? Because how are you gonna calculate these? Well, it will give you some outputs, yeah. Will it? But outputs of what? Still quite high level, so I'm not so sure how are we gonna integrate these with, you know, with this stuff in here. It's a bit uncertain, but okay, we're gonna keep these two boxes out of the picture for now. Get the batch encoding done, and then see how we can move forward somehow. I really want to do this from scratch. I'm really gonna. I'm really thinking to just do the whole. This is gonna be okay, yeah, but I'm thinking to do the whole optimization stuff really by hand, not using anything from PyTorch. It's gonna add definitely a lot of more time to the project, but I think that is kind of a good exercise. See you next time.